When a massive star collapses into a neutron star, it leaves behind one of the strangest objects in the cosmos. From afar, it seems simple, a tiny sphere spinning in space, only the size of a city. But inside, matter is crushed so hard it becomes something we've never seen on Earth. At its core, the rules of physics start to bend. Nuclear labs and particle accelerators can only imitate these extreme pressures for a split second, but even that glimpse tells us something crucial. This is where matter itself begins to change. What happens when atoms are crushed past their limits? Do new exotic particles appear, or do neutrons split apart into quarks? Could a neutron star's core mirror the conditions that existed just moments after the Big Bang? We don't yet know, but every new observation pulls us closer to answers that could rewrite what we think reality is made of. From the outside, a neutron star looks calm, a flashing dot spinning like a cosmic lighthouse if it's a pulsar. But it's born from chaos, the violent collapse of a star 8 to 20 times heavier than our Sun. When its fuel runs out, gravity wins. The star implodes, smashing protons and electrons into neutrons until the pressure finally stabilizes, leaving behind a city-sized sphere only 10 to 20 kilometers across. Inside, though, lies an alien world, unlike anything in the universe. Scientists describe the inside of a neutron star as a series of layers, each one revealing stranger forms of matter. At the surface lies the outer crust, just a few hundred meters thick. You can think of it as the star's skin, where atomic nuclei are still recognizable, surrounded by a haze of electrons. But even here, it's far from normal. The density is so extreme that any material we know, even steel or tungsten, would crumble instantly. Every atom is squeezed tight against its neighbor, creating what many believe is the strongest material in the universe. This unbreakable crust is what allows the star to survive such unimaginable gravity. Go a little deeper, and you reach the inner crust, where things get truly bizarre. The pressure becomes so intense that neutrons escape their atomic prisons, leaking out and filling the gaps between nuclei, a process called the neutron drip. This changes the crust into something not quite solid, not quite liquid, a weird mix behaving like both crystal and superfluid. We can't recreate this environment on Earth, so scientists rely on pulsar data to understand it. Some pulsars suddenly speed up, an effect called a glitch. These glitches might happen when the inner crust interacts with the mysterious superfluid beneath it. One of the clearest examples is the Vela pulsar, which has shown repeated glitches, strong clues that something extraordinary is happening in that boundary zone. Below it lies the outer core, the dense heart of the star where neutrons rule, but they aren't alone. Deep inside the star, protons, electrons, and muons mix with the neutrons, and under such crushing pressure, they begin to behave in strange, unified ways. The neutrons are thought to form a superfluid, flowing with zero resistance, while the protons become a superconductor, carrying electric currents without losing any energy. These aren't wild theories. Both nuclear physics and space observations back them up. The way neutron stars cool over time fits perfectly with what scientists expect if their cores contain superfluid neutrons that change how heat moves through the star. This outer core is also where a neutron star's magnetic identity is forged. Some are born with weak fields, while others become magnetars, monsters with magnetic forces strong enough to tear atoms apart from thousands of kilometers away. The difference likely depends on how electrical currents twist and flow through the superconducting layers of the outer core. In other words, this zone acts as the star's engine, powering many of the dramatic effects we detect from light years away. And then comes the inner core, a realm where science steps into the unknown. The density here is several times higher than that of an atomic nucleus, far beyond anything we can replicate on Earth. It's possible that even neutrons can't survive intact. Some theories say heavier particles, called hyperons, could form. Others suggest the neutrons might dissolve entirely into quarks, their most basic building blocks, turning the inner core into a dense soup of quarks and gluons, much like the newborn universe right after the Big Bang. We still don't know which theory about the inner core is correct, but we do know one thing. It decides how massive a neutron star can grow before collapsing into a black hole. That's why discoveries like PSRJ 0740 plus 6620 are so critical. This monster packs more than twice the Sun's mass into a sphere barely a few kilometers across, pushing physics to its breaking point. Its existence proves the core must be incredibly stiff and resilient, ruling out weaker models that predicted softer matter inside. Each layer of a neutron star leaves its mark on what we can see. The crust shapes how pulsars spin and glitch, the outer core controls cooling and magnetic strength, and the inner core sets the ultimate mass limit. By linking these surface clues to what's hidden inside, astronomers are turning neutron stars into natural laboratories, extreme testing grounds for the laws of physics. But even with all our data, the inner core remains a mystery. Down there, density climbs to several times that of an atomic nucleus. For perspective, a sugar cube of nuclear matter would outweigh a mountain. Multiply that by 3, and you're close to what's happening inside. At those depths, our usual idea of matter, made of protons and neutrons, might simply break apart, revealing an entirely new state of reality that we've never witnessed on Earth. One leading theory is the rise of hyperons, particles similar to protons and neutrons, but containing at least one strange quark. According to nuclear physics, when density becomes extreme enough, it's actually more energy efficient for these exotic particles to appear. But their presence creates a serious problem. If too many hyperons form, the matter inside the star softens, meaning it becomes easier to compress. That would make it nearly impossible for a neutron star to hold up large masses. Yet, observations of giants like PSRJ 0740 plus 6620, which weigh more than twice the Sun, show that these stars somehow resist collapsing. This contradiction is known as the hyperon puzzle. If hyperons are real, something else inside the core must counter their weakening effect. One possible answer involves meson condensates, strange collective states made from particles called mesons, which consist of a quark and an antiquark. Under the right pressure, mesons such as pions or kaons could merge into a dense, superfluid-like form that changes the pressure balance and cooling speed of the star. Scientists are already studying neutron star cooling patterns to search for signs of these hidden phases, but for now, the evidence remains indirect. The most extreme possibility goes even further, that neutrons and protons themselves break down completely. In this scenario, the inner core would transform into quark matter, where quarks are no longer trapped inside particles but move freely in a dense, liquid-like soup. If true, this would mean the centers of neutron stars hold the same kind of matter that filled the universe microseconds after the Big Bang. If quark matter truly exists, then the heart of a neutron star would mirror the universe just microseconds after the Big Bang. Some theories even describe hybrid stars, with an outer layer rich in neutrons wrapped around a quark-filled core. Others go further, suggesting the existence of strange quark matter, made of up, down, and strange quarks, which could be more stable than ordinary atomic matter. If that's true, entire stars made entirely of strange quark matter could be scattered across the cosmos, though none have yet been confirmed. The problem is that all these exotic forms, from hyperons to meson condensates to quark matter, leave behind only faint, easily confused signals. The differences appear in how squishy or compressible the star is, how it behaves during violent mergers, or how it slowly cools over time. New tools are helping crack the mystery. Gravitational wave events like GW 170817, the collision of two neutron stars, are offering vital data. The way those stars distorted each other before merging depends directly on how stiff or soft their cores were. But even with this progress, we still don't know for sure which, if any, of these exotic states actually exist. That uncertainty isn't a failure of science. It's exactly what makes neutron stars so fascinating. They push our theories to their limits. If we ever confirm quark matter inside one, it would mean we've found a relic of the universe's earliest state. If hyperons are proven real, it would rewrite what we know about strong nuclear forces. And if none of these strange states exist, it would mean ordinary nuclear matter can survive pressures far greater than anyone imagined. We can't dig into a neutron star or build one in a lab, so every clue must come from their signals, their mass, radius, cooling, and gravitational waves. Each new measurement is like a piece of a cosmic puzzle, bringing us one step closer to understanding the most extreme objects in existence. Piece by piece, every new observation helps build a clearer picture of what hides inside a neutron star's core. One of the most powerful tools for this is NASA's NICER telescope, mounted on the International Space Station. It measures X-rays from pulsars with remarkable accuracy, allowing scientists to determine their size and mass like never before. Take P-SRJ 0030 plus 0451, for instance. Its data gave us one of the first reliable radius measurements. Knowing both its mass and radius allowed researchers to narrow down which equations of state are possible. If the core were too soft, the star would shrink; too stiff, and it would be much larger. The real results landed between those extremes, showing that neutron star cores are neither fragile nor unyielding, but something in between. Mass is just as revealing. The record-breaking PSRJ 0740 plus 6620 weighs more than twice the Sun's mass, yet hasn't collapsed into a black hole. That means its core must resist unimaginable pressure, instantly ruling out many models that predict exotic matter but can't sustain such weight. Discoveries like these constantly force scientists to refine their theories about hyperons, quark matter, and other dense states. Gravitational waves have added another dimension to this hunt. When two neutron stars spiral toward each other and collide, they send out ripples in space-time that we can now detect from Earth. The first of these, GW170817, revealed how neutron stars stretch and deform under intense tidal forces during a merger. This property, known as tidal deformability, directly exposes how stiff or flexible the matter inside them really is, giving scientists another key to unlock the secrets of the densest objects in the universe. If a neutron star's core is soft, it squashes more easily during a merger, creating a stronger tidal signal. If it's stiff, it resists, producing a weaker one. By matching these gravitational wave patterns with theoretical models, scientists are narrowing down what the core is really made of. Even the strange behavior of pulsars offers more clues. Some pulsars suddenly speed up, a phenomenon called a glitch, caused when the star's superfluid interior transfers angular momentum to its crust. Studying these jumps helps scientists understand how that ghostly, frictionless fluid moves beneath the surface. The Vela pulsar is a perfect example. Its frequent glitches have turned it into a natural lab for studying the superfluid nature of neutron star interiors. Cooling behavior gives us more evidence. Young neutron stars lose heat fast, and the exact cooling rate depends on what particles lurk inside. In the Cassiopeia, a supernova remnant, one neutron star showed a surprisingly sharp drop in temperature, exactly what would happen if its core were filled with superfluid neutrons. That single observation became one of the strongest signs that these strange states of matter are real. When combined, X-ray radius measurements, mass data, gravitational waves, pulsar glitches, and cooling rates, all these clues form a grand puzzle. Alone, each piece tells only part of the story, but together they reveal the hidden physics of matter under impossible pressure. The picture isn't complete yet, but with every new observation, it sharpens, bringing us closer to finally understanding what lies inside the densest stars in the universe. Despite all the breakthroughs, the core of a neutron star is still one of the biggest mysteries in physics. Every new discovery helps, but the main questions cut straight to the heart of matter itself. The first puzzle is the equation of state, the link between pressure and density inside the star. For normal matter, this relationship is well understood. But when densities reach several times higher than those of an atomic nucleus, the rules start to blur. Competing theories give very different answers. Some say the core is stiff and resists compression, others claim it's soft and squeezes more easily. Both can explain parts of the data, and the challenge is finding enough evidence to prove which one is true. Then comes the question of exotic matter. If things like hyperons, meson condensates, or quark matter truly exist inside these stars, they should leave distinct traces. The problem? Those effects are incredibly subtle, and they often mimic each other. Both hyperons and quark matter, for instance, tend to soften the equation of state, making the star slightly smaller and more compressible. Our instruments today simply aren't precise enough to tell them apart. That makes it difficult to know whether scientists are seeing hints of new physics or just pushing the limits of what we already understand about nuclear matter. Laboratory experiments, like heavy ion collisions, can briefly recreate extreme conditions and offer clues about how matter behaves at high density. But even they fall short of the relentless, crushing pressures inside neutron star cores. That's why these mysterious objects remain such powerful, frustrating, and fascinating testing grounds for the laws of the universe. The data from nuclear physics experiments is incredibly valuable, but it only tells half the story. To truly understand neutron stars, scientists must combine those results with astronomical measurements, a task that's anything but simple. The two datasets don't always line up perfectly, leaving frustrating gaps that can only be filled with sharper theories and more precise observations. One of the biggest challenges is measurement uncertainty. Determining a neutron star's exact mass and radius is notoriously difficult, and even tiny errors can flip our conclusions about what's inside. NASA's NICER mission has made major progress, but even its most accurate results still leave room for several competing models to survive. Gravitational wave data adds another clue, yet remains limited. The famous GW170817 merger gave us priceless insight, but it was just one event. To truly separate fact from theory, astronomers will need dozens of such collisions, each captured in fine detail. Then there's the mystery of cooling, the rapid temperature drop seen in the Cassiopeia. A neutron star seems to confirm that superfluidity exists deep inside. But cooling rates depend on countless factors, from exotic particles and superfluid gaps to how neutrinos carry energy away. Without more young neutron stars to compare, it's hard to tell whether Cassiopeia A is typical or a rare exception. Finally comes the question of limits. How massive can a neutron star get before gravity wins and it becomes a black hole? Discoveries of stars heavier than 2 suns have already rewritten the rules. But if astronomers ever find one even denser, breaking every theoretical boundary, it could shatter long-held ideas about matter, gravity, and the point where the universe itself says no more. If astronomers never find neutron stars heavier than the ones we already know, it might mean nature itself enforces a strict upper limit, possibly because exotic matter inside makes the core too soft to support more mass. These uncertainties remind us how early we still are in truly understanding what lies within these stellar remnants. We're slowly piecing together the puzzle, but the picture is far from complete. Every new measurement adds a constraint, yet countless possibilities remain. That's what makes neutron stars so captivating. They're living laboratories, holding answers to questions no experiment on Earth can fully solve. The real challenge is learning how to decode the faint clues they send us across space and linking those signals to the unseen chaos inside. At first, studying neutron star cores might sound like a niche field for astrophysicists, but it actually connects many branches of science. These stars stand at the crossroads of nuclear physics, particle physics, astrophysics, and cosmology, uniting them in a single cosmic mystery. Understanding what happens inside a neutron star isn't just about stars. It's about testing the foundations of matter itself and how the universe operates under the most extreme conditions imaginable. On Earth, even the most advanced machines, like the Large Hadron Collider, can only smash atomic nuclei together for fractions of a second, briefly mimicking the pressures found inside these stars. A neutron star, by contrast, keeps that crushing density for millions of years. It's a natural experiment written across the sky, offering a glimpse into matter pushed to its ultimate limit, a frontier where physics itself is still being rewritten. A neutron star is like a permanent experiment set up by nature itself. All we have to do is learn how to read its results. These stars form a bridge between nuclear physics and astrophysics, pushing the same forces that bind atoms on Earth to their absolute limits. If exotic states of matter like quark matter or hyperons really exist inside them, it would mean our current understanding of the strong nuclear force, the force that holds atomic nuclei together, is incomplete. Cracking this mystery wouldn't just change astrophysics, it would reshape what we know about the matter that makes up everything around us. Neutron stars also play a key role in gravitational wave astronomy. When two of them collide, the impact doesn't just ripple through space-time. It forges heavy elements like gold and platinum. These cosmic mergers depend directly on what's inside each star. The stiffness of their cores determines how long they spiral before impact, how much matter they eject, and how bright the resulting explosion, known as a kilonova, becomes. Studying these cores means we're also uncovering the origin of Earth's rarest elements. And while this might sound like distant theory, history shows that discoveries like these often have surprising real-world impacts. The principles of superfluidity and superconductivity, first theorized in neutron stars and later confirmed on Earth, now power everything from quantum computers to MRI technology. By understanding how these strange states behave in the most extreme environments in the universe, we could unlock ideas that transform technology right here at home, proving once again that the secrets of distant stars can shape our everyday world. More than anything, neutron star cores remind us how little we truly know about the universe. They prove that the matter we take for granted, protons, neutrons, electrons, isn't final or fixed. Under unimaginable pressure and heat, matter transforms, reshaping itself into something deeper and stranger than anything we've seen. Inside these cosmic furnaces, ordinary atoms give way to exotic states, perhaps vast seas of free quarks or other unknown particles echoing the birth of the universe itself. Neutron stars are nature's quiet reminder that the story of matter is unfinished, a silent challenge from the cosmos to keep searching, questioning, and imagining. When we describe them in numbers, masses greater than the sun packed into a sphere just kilometers wide, density so high that a teaspoon would outweigh a mountain, it's easy to forget what those numbers really mean. They point to a world where physics as we know it begins to break down. At the center of each neutron star lies a region we can't see, yet everything we can observe depends on it. The way pulsars flash, the way neutron stars cool, spin, and even merge. All of it traces back to that invisible, chaotic heart. Despite all the progress, the core remains more mystery than fact. Evidence suggests that neutrons behave like superfluids and protons act as superconductors, creating strange forms of energy flow. We also know the core must be incredibly stiff, strong enough to hold more than 2 suns worth of mass without collapsing. And deep within, hints of quarks or hyperons might be lurking. Signs that even now, the universe is still revealing new layers of reality we've only begun to glimpse. None of these ideas are proven beyond doubt. Each time one theory fades, another rises, keeping the mystery alive. But that's not a weakness of science, it's what drives it forward. Neutron stars aren't just strange objects in space. They're nature's laboratories, pushing physics to its limits and connecting the tiniest particles with the grandest cosmic events. Inside them, the behavior of quarks, the mergers of stars, and the creation of heavy elements are all part of the same story. Through these stars, the universe gives us a direct glimpse into the conditions that shaped everything, from the first seconds after the Big Bang to the forces still sculpting galaxies today. The truth of what lies inside a neutron star's core won't be solved by one theory or one observation. It will take years of precise measurements, new gravitational wave detections, and smarter models to finally piece it all together. Every discovery narrows the possibilities, but also reminds us how much remains unknown. For now, the core of a neutron star stands as one of astrophysics' last great secrets, a place where our understanding of matter itself bends and nearly breaks. The fact that we can ask these questions proves how far we've come. The fact that we can't yet answer them shows how much further we still have to go. That balance between knowledge and mystery is what keeps neutron stars at the heart of modern science, and what makes them so endlessly fascinating to anyone searching for the universe's deepest truths. If you enjoyed this breakdown and want to stay updated on every new space discovery, make sure to like, subscribe, and share. Your support helps keep these cosmic explorations going. Thanks for watching, and as always, keep looking up.